Class 11th Chemistry, Unit 7 Equilibrium, and in this video we are going to discuss about relationship between equilibrium constant K, reaction quotient Q and Gibbs energy G. Delta G is equal to delta G standard plus RT ln Q, where this represent the standard Gibbs energy change, Q is the reaction quotient, and this Ln represent the natural log. Okay. At equilibrium, when delta G is equal to 0, then Q will be equal to Kc. So we can write delta G is equal to delta G standard plus RT ln K, and this is equal to 0. That is, this delta G is equal to 0. So we can write delta G standard is equal to minus RT ln K. Clear? Now, when this ln, that is natural log, is converted into the basis of 10, then ln is replaced by log, log, and this is multiplied by 2.303. So we have delta G standard is equal to minus 2.303 RT log K. You have to remember this relationship. This is used for the calculation purpose in numericals. Okay. Now, if we rearrange this relationship, then we can write this ln K. This is equal to minus delta G standard divided by RT. Now, if we take the anti-log of this equation of both sides, okay, if we take the anti-log of this equation, then we will get K is equal to e raised to the power minus delta G standard divided by RT, where this, again remember, when again we take the log of this equation, okay, we will get this one. Again, this E for the natural antilog. Okay. Now, from this relationship, just see, if delta G standard is less than 0, then this minus delta G standard divided by RT, this is positive. And when this is positive, this E raised to the power minus delta G standard by RT, this is greater than 1. And so K will also be greater than 1. So we can say reaction is spontaneous in forward direction and products are present predominantly. This relationship correlate the delta G with K. Clear? In the same way, if delta G standard is greater than 0, then minus delta G standard divided by RT is negative, and this E raised to the power minus delta G standard by RT, this is less than 1, and this make K is less than 1. So reaction is non-spontaneous in forward direction and only a very minute quantity of product is formed. Clear? Now we will discuss some numericals which are based on this formula. Delta G standard is equal to minus 2.303 RT log K. Okay, and we will also discuss how to solve this log. Problem 7.10. The value of delta G standard for the phosphorylation of glucose in glycolysis is 13.8 kilojoule per mole. Find the value of Kc at 298 Kelvin. We use this relationship. Delta G standard is equal to minus 2.303 RT log Kc. Okay. And in this case, delta G is given and this is given in kilojoule per mole. Okay. That's why we will convert this into joule per mole by multiplying 10 to the power 3. And why we are converting this kilojoule into joule? Because we are using the value of R in joule per mole. R is 8.314 joule per mole per Kelvin and temperature is given 298 Kelvin. This can be written like this. log case is equal to minus delta G standard divided by 2.303 RT. Put the value. Okay. Now this 13.8 into 10 raised to the power 3. This will be power. Okay. Divide by 2.303 into 8.314 into 298, and if we solve it we will get minus 2.4186. This is the value of log Kc. And when we want to find out the value of Kc, we have to take the anti-log of this number. So we have written Kc is equal to anti-log of minus 2.4186. Now again remember, there is a one separate video how to solve log and anti-log. Watch it. Okay. In short, it is explained log and anti-log in that video. Again remember, for negative number we can't see the anti-log. So first of all, this, and again anti-log table is starting from decimal. That's why this number we have to convert into positive after the decimal. Okay, just see, we have to find out the anti-log of this number, and this can be written as minus 2.4186 is equal to minus 2.0000 minus 0.4186. I think you will not feel any difficulty to write this number like this. Okay, and when we subtract 1 and add 1, there is the no net change in the result, because same number when added and same number is subtracted, there is a no change. Okay, that's why we will subtract minus 1, we will subtract 1 from this. Okay, so we'll get this become minus 3, and we add 1 in this number. This is 1 and this is minus 0.4186. When we will add, we will get this 0.5814, and this is in positive number. Clear? And this is negative, and this negative is written as bar. This is 3 bar. Bar means this is minus 3. 0.5814. Again remember, this 0.5814, this is positive. Yeah, so we will see this number in the anti-log table. Now in anti-log table, first we'll see this is 0.58. Like see, this is part of anti-log table is there. This is 0.58, first 2 digit. Then third digit is 1. Okay, that's why 0.58, and this is 1. This is 3811. Okay, then fourth digit, that is 4. You will see this 4 mean difference, and this 4 is added in this. So we will get this is 3815. Okay. Now what we will do for this bar 3? Again, there is a one shortcut method. From left hand side, after 1 digit, put decimal. It is 3.815 and multiplied by 10 raised to the power minus 3. Okay, this 3 is written like this. So our net result is 3.815 into 10 to the power minus 3. Okay. Now see one more question. Problem 7.11. Hydrolysis of sucrose gives sucrose plus H2O gives glucose plus fructose. Equilibrium constant Kc for the reaction is 2 into 10 to the power 13 at 300 Kelvin. Calculate delta G standard at 300 Kelvin. This is the formula which we will use. Delta G standard is equal to minus 2.303 RT log Kc. Okay. Now in this case, this K is given 2 into 10 to the power 13. R, gas constant 8.314 joule per mole per Kelvin, and temperature is 300 Kelvin. Put the value. Delta G standard is equal to minus 2.303 into 8.314 into 300 into log of 2 into 10 to the power 30. Clear? Now first we will solve this. Log 2 into 10 to the power 13. Just see, this can be written like this. Log 2 plus log 10 to the power 30. If you remember, if numbers are given like this is n into m in the multiplication, then if we take the log of this this will be written as log n plus this is log m. Clear? Now again, if we take the log of any this exponent, then this exponent will come before log. So we can write this will be log 2 as usual, and this is log 10 power 13. 13 will come before log, so 13 log 10. Now we will see the value of log 2. Again, remember in the logarithm table, this vertical column will start from the first 2 digit, but in this number we are having only the 2 digit, so this can be written as, put the decimal and you can assume many zeros, 2.000. Okay, so before looking in the logarithm table, before decimal there is a 1 digit in the number, subtract 1, so we will get 0. Okay, then forget this decimal. Now we'll see the value of 20 in 0. So 20, this is the 20 in vertical column, this is 0. Okay, and there is no need to see mean difference because mean difference start from the 1. So this is 3010. So we have put this is 0.3010. This is the value of log 2. Now plus this is 13. Now value of log 10 is 1. How? Now in this case only 2 digits are there. So you can write this is 10.00 and so on. Before looking into the logarithm table, before decimal there the 2 digits are there. So subtract 1, we will get 1. Now put point. Now see the value of the value of 10 in 0 in the logarithm table. So this is 10 and in 0 we will get the 0. So simply we can say value of log 10 is always 1. So this is multiplied by 1, and if you solve it we will get 13.3010. Now put this is the value of log 2 into 10 to the power 13, and if you multiply all these numbers we will get this one in joule per mole, and if we convert this into the scientific notation we will get minus 7.64 into 10 to the power 4 joule per